Hello all, well here we are, last note of SPH3U, last note of the semester for us, chapter 18. Now chapter 18 is the reverse of chapter 17. Chapter 17 was looking at how we can use electricity to create magnetism. Chapter 18 is about how we use magnetism to create electricity. Right, so that's the goal here, again. Just like I had said in the previous chapter that the discovery of the electromagnet and the motor principle changed the world, this is the opposite scenario, and it likewise has changed the world and continues to change the world in our lives on a daily basis. So this is where the world is changing. This is where we are in 2020, and this is where we are looking for bigger and better ways of creating electricity for our homes, as well as finding ways of using the electricity we have to do more with a smaller amount of electricity, so we don't need to generate or use as much electricity. Okay, so chapter 18. For the record, before I get started, I'll say this twice. Chapter 18 will not be on our test this week, but I encourage you to watch through this video because it will talk to you about how our electricity is generated and delivered to our homes and all the aspects of our electric generating system and the power grid. Okay, so in order to make electricity, I need to have a changing magnetic field. Okay, I need the magnet to be moving. Now, that being the case, as long as the magnet continues to move, I will continue to make electricity. Now, in order to get the maximum amount of electricity, I'm not just going to use a straight conductor of conductor. I'm going to use a coil, and that will give me more opportunity for the conductor to be more of the conductor to be affected by the magnetic field. Not only am I going to use a coil, but I'm going to maximize my number of loops of wire on the coil. I'm going to maximize the rate of change of the magnetic field. In other words, I'm going to move it faster and faster and faster. And I want the strongest possible magnet to make this all work. So, moving a magnet past a conductor or moving the conductor past the magnet, either one is going to create the movement of electrons or current in the conductor. Now, if I sit the magnet down on top of the conductor, even a strong, super strong electromagnet, if it's not moving, there will be no electrons moving in the conductor. So in order to make electricity, in order to produce current, I need the magnetic field, which is in proximity to the conductor, to be moving. Now today in our lives, there are lots and lots of opportunities or applications for electromagnetic induction. We have induction stoves. Again, my son has one at home where we use a changing magnetic field inside his stove, which will ultimately create the current, electricity, in the pot, which will ultimately generate a lot of heat. And because it's such high resistance, there's very low current, so it's not dangerous, but it is a very efficient way of heating. And again, that's historically I would have said there were two ways to make a stove. One is a gas stove and one's an electric stove. Today we've got induction cooking also. Our metal detectors work the same. By moving a magnet past a conductor, we can actually generate fields which are measurable, and we can actually use those to tell us when there's a metal present. And then we have induction chargers, again, where we don't plug, you just sit your phone down on the induction charger, and by moving a magnetic field inside the charging base, it will charge our phones. And the same thing with something like an electric toothbrush or other types of electric devices. where we use just set the device close to the charging base, and it will the movement of the magnetic field will ultimately generate the electricity which is used to charge the device. Now, a physicist named Lentz gave us what is now known as Lenz's law, and it's a way to try and decide. So, in a wire or in a conductor, electrons have two possible directions, right? They can be moving this way or that way. We've got our only two possibilities here. Lenz's law is the way that we determine which way the current is going to be flowing inside the conductor. Now, again, we've got this picture's upside down, but again, if you look in our textbook, you'll see there's a right-hand rule for Lenz's law, and the right-hand rule basically talks about if I have a bar magnet here, and I've got a coil here, if I push the bar magnet into the coil, right, as it's going in, it will cause the electrons and the current to move inside the coil here. Once it's in there, the electrons stop moving. But if I pull it back out again, the electrons will be induced to move again. So every time the magnet is moving past the coil, either into or out of the coil, it's going to cause the electrons to move. As it's going in, it causes the electrons to move in one direction, and as it's coming out, it causes electrons to move in the opposite direction. Again, this should be ringing a bell in terms of AC, alternating current electricity. Pushing the magnet in, pulling the magnet out, pushing the magnet in, pulling the magnet out, and the electrons change direction, back and forth, back and forth. Now, again, lots and lots of applications. The textbook talks a little bit about drop zone at Canada's Wonderland, and as you are falling, as you get towards the bottom of the ride, it induces a current. The magnetism moving past the coils induces a current, which activates a brake system, which ultimately slows down the ride. So, as frightful as it is when you're in free fall at the very top of the ride, you will actually not go crashing to the bottom at the very when you get to the end of the ride. Okay, so let's talk about AC, alternating current electricity, for a moment. And like I said a moment ago, the goal here is to be moving the magnet into a coil and out of the coil in succession. And as I move it in and out, in and out, in and out, I'm going to end up creating alternating current electricity. Now, Thomas Edison came up with a DC generator that provided electricity or current that had only one direction, right? And that one-way flow of electrons was one possibility. So again, be thinking about a time before we had electricity in our homes, and we've got these two people, Thomas Edison and Nikola Tesla, who have developed two different ways to make electricity. And Thomas Edison was by far much more well known, had a great reputation. Nikola Tesla was the newcomer on the scene, and at the end of the day, as you'll see in about 10 minutes or so, Nikola Tesla won, which is why we have alternating currents in the plugs of our homes and not direct current. So because we have alternating current, so Edison's DC generator had a commutator which was similar to what we had in a DC motor, and ultimately what that allowed was the one-way flow of electricity. Now, if I keep moving down here, so what happens today in North America is we have electricity that goes forward and backwards, and forward and backwards, and forward, and it keeps going back and forth. Okay, it has one cycle of this wave every 1/60th of a second, 2/60ths of a second, 3/60ths of a second. Okay, so we talked about this when we did the ticker tape lab way back in the first week of the semester, and we said because the electricity changes direction 60 times per second, goes through a full cycle, 60 times per second. When it gets to the end of the cycle, before it can go back in the opposite direction, it's got to stop, right, and then change direction. And because of that, the magnet in the ticker tape timer would go off, and it would reactivate the electromagnet every time the current was reactivated. Now, that being the case, that's what happens in North America, right? We've got a system that has 60 hertz, right? 60 changes, 60 cycles per second. And today, what we have in our homes is a service line that comes into our homes, right? The service line brings the electricity that I need, which has a frequency of 60 hertz. It's alternating current, and basically that comes in two separate wires. I've got the two hot wires. One's the red wire. One's the white wire. One's the one's the red wire, and one is the black wire. Okay, and they both are delivering 120 volts of potential. Now, I've got a third wire coming into my house, which is the white wire, and then I have a fourth wire also coming in, which is my ground wire, which is basically, again, remember, just a protective mechanism. So, if I use either the red or the black with the white, I'll end up with 120 volts going to my plug. If I actually use both the red and the black together, I get the 120 volts of potential from the one line and the 120 volts of potential from the other, and I can actually have circuits in my home here in Hamilton that have 240 volts if I use both the red and the black. But like I said, I'm sure I'd say 99% of the things in my house need 120 volts. The only things in my house that need 240 volts are my electric dryer, my old electric stove, I have a gas stove now, and my air conditioner. Right? Those things need 240 volts. They need the extra energy to run. Those things have a special kind of wire that goes to them that can handle the extra voltage, the extra current, and provides the extra energy to my device. Now, we talked before about safety mechanisms in our home electrical systems. We've got fuses, we've got circuit breakers. Right, circuit breakers and fuses basically prevent too much electricity from going through the wires in my house, and they will shut off the electricity if too much tries to go down the line. In 2020, it is law to have GFIs in our bathrooms and kitchens and laundry rooms and outside. Anytime I've got water nearby a plug, within 1 meter of a plug, I have to have a GFI outlet. Those are the ones that you see in the school that have the plugs, and then they got the two little buttons on them. One is for turning the power on, and one is for shutting the power off, or for testing the system. And basically what it does is it shuts the electricity off, and you think, well, a fuse and a circuit breaker would do the same thing, but by the time the fuse or the circuit breaker detect there's a problem, whoever it is that's being exposed to the electricity may be getting exposed to too much electricity. So we have GFIs in our bathroom, and they basically, the second the system recognizes that there's a short circuit, it will automatically shut off the power, and it can be reset very, very quickly if we've just tripped it by putting maybe too many things on that circuit. There are new types of circuit interrupters called arc fault circuit interrupters, and again, they are even more sensitive than the GFIs, but the GFIs are kind of the standard today. I'm not going to go through the AC generator or the DC generator, right? But the AC, remember the AC has alternating current. Now, this is part of the trick here. This thing right here is called a transformer, right? The transformer basically is an iron ring, and what happens is electricity comes in on one side. So let me get rid of that. Electricity comes in on one side, okay, my primary coil, and electricity goes out on the other side. The electron flow or conventional flow on this side is separated from the electricity on this side. Right? They're not connected. But what happens is because the electricity on this side is going back and forth, back and forth, back and forth, what it does is it creates a magnetic field that changes as the electricity is coming through faster, then stops, then speeds up, and then stops, then speeds up and stops. It's constantly changing, but it's also changing direction. So what that means for this is this becomes a magnet which is going to be north and south at one point, and then it's going to become south and north when the electrons are going back the other direction. Then it's going to become north and south again. So this thing is a magnet that's flipping back and forth, back and forth, back and forth. As the electrons here are changing direction, as electricity is changing direction because of the alternating current, this magnet is flipping back and forth. As it flips back and forth, this changing magnetic field causes the electrons on the secondary coil to move. Now it turns out that the number of loops that I have on this side compared to the number of loops on this side change the voltage and the current. The power coming in on this side is going to be equal to the power on this side coming out. Now, if the power is constant on both sides, but power, we know, is equal to V times I, and V times I, if the voltage is higher on one side, I can lower the voltage on the other side, but that means I have to increase the current. Or vice versa. If I increase the voltage on one side, I decrease the current. So this transformer here is a way of changing the speed of the electron flow and changing the amount of energy that each electron is carrying, changing the voltage or potential of those electrons. Now, if I've got a transformer that has higher voltage on one side and slower velocity, slower current, so high V and low current on one side, I can have low voltage and high current on the other side. Now, the beauty of this is, hypothetically, if the power in is equal to the power out, that's called a perfect transformer or an ideal transformer. And in the ideal transformer, I can change the speed of electrons. Now remember, when electrons move faster, there's a greater loss of energy. So low current is ideal. And if I have electrons that have low current but are carrying a massive amount of energy, when they get to the other end of where they're coming from, so let's say they're traveling, think about those overhead lines that you see out in the country, let's say over St. Catharines, that are bringing electricity to Hamilton, right? They're moving slowly, right? I have low current because if it's going too fast, it's going to heat up the wires, and it's going to basically dissipate some of the energy as heat. And by the time it gets to Hamilton, I will have lost a bunch of my energy. So I want to slow them down, but to do that, I'm going to increase their voltage. Now, high voltage is very, very dangerous. So as it gets to Hamilton, I don't want those high voltage electrons here, so I'm going to lower my voltage. Right? And as I lower the voltage, it's going to increase my current. Right? Now, that increased current I can send in all these different directions, to go down different streets, to go into different homes, to go into all these different places it has to go. I'm going to divvy it up, right? And it's at a lower potential, so it's not as dangerous as the high voltage electrons that I was using on the other side. So I've got two types of transformers here. I've got a transformer that increases the voltage and slows down the current, and I've got called a step-up transformer. It increases the voltage, and then at the other end, here in Hamilton, I've got something called a step-down transformer that takes those really high voltage electrons that are in those overhead wires and drops the voltage down to a safer level, and then spreads them out so they can go to all the different places that they need to go at the other end. So I've got step-up transformers and I have step-down transformers. And again, it's a whole bunch of math that we're not going to get into. Okay, but just recognize that as Edison and Tesla were both working together, because of this whole use of the transformer, Tesla found a way to get electricity to the city of Hamilton very, very efficiently by using AC at high voltage and low current, so it could get here with very, very minimum amount of loss, and then change it back to low voltage, high current, so I could send safe electrons to so many different people. And ultimately, Tesla's way of doing things turned out to be much, much more cost effective. So, so let's just come down to our last picture, our last image of the year, and it shows the Surratt-Beck hydroelectric generating station down here at Niagara Falls. Right, it generates AC electricity because of the movement of water, turning turbines, moving magnets, electromagnets past coils, or moving coils past electromagnets, generating AC electricity. That AC electricity is produced at about 20,000 volts, right? And here in Hamilton, I need my 240 volts. Here in my house. So to get this from 20,000 volts here to Hamilton, I'm going to take the 20,000, I'm going to step up the voltage using my step-up transformer to about 500,000 volts. They're going to travel slowly to Hamilton, right, through overhead wires, and then once they get into Hamilton, they're going to get to a local transformer station, right? The local transformer station, again, we see them around. There's a number of them. There's one down just on Cannon Street. They're all over the place. So these transformer stations take the 500,000 volt electrons, step them down to closer to 50,000 volts or less, and then on our streets we have either these canisters, which are transformers, which are step-down transformers, or we have the green boxes that we sometimes see in front of newer areas, and those are step-down transformers also. And what they're doing is they're taking the electrons that have still too high a voltage, and I'm stepping them down again to a lower voltage. So again, notice that I've got a lot of coils, loops on one side, and then smaller on this side, and then to get from 4,000 down to the 120 that I need to go into my two lines in my house, I've got the large number of loops on one side of my transformer and a small number of coils on the other side, and that's a step-down transformer too. Then ultimately I've got the 220 volt lines that'll ultimately end up going into a person's home. Right, so I'm going to use transformers and the notion of AC electricity to effectively move electricity across this massive country that we live in. Right, going back not too long ago, Niagara Falls produced most of the electricity in Ontario. Right, and that being the case, it had to travel a long way. Ontario's a big place, so we had to get electricity from Niagara Falls to Hamilton, to Toronto, to Ottawa, to Sudbury, to Thunder Bay, right? 15 hours driving to get to Thunder Bay, and I had to get electricity there, and if I was using direct current and having to get it all the way up there, I'd be trickling energy away the whole time. By the time it got there, there'd be so much lost that it would be very inefficient. By using AC electricity and step-up and step-down transformers, I can move small numbers of very high voltage electrons from point A to point B. Right? They don't have to go too fast because they're carrying so much voltage, so much energy. When they get to the far end, I can just take each coulomb of electrons and take all the energy that they were carrying and divvy it up over a large number of coulombs so that they can go into our homes to do what we need to do. All right, so that is chapter 18. As I said at the beginning of today's note, this chapter will not be on our test next week on Wednesday. I originally had thought, up until about an hour ago, that I was going to include topics from this chapter in our test on Wednesday, but I think I'm just going to say, you know what, let's just go with chapter 16, and from chapter 17, just understand how electromagnets work, the basic premise of magnetism, the right-hand rules for conductors, the right-hand rule for coils and solenoids, the right-hand rule for the motor principle, and then I think that's going to be enough. Maybe more than enough. So normally I would have a test on chapter 16 on its own, and then a test on chapters 17 and 18 on their own, but as I just said, I'm not going to put chapter 18 on our test. So that's physics, right? So I'm not going to go into a long discussion of what it is that we've done in this course, but just recognize we've covered a massive amount of ground, most of it having to do with motion of something. Motion of electromagnetic waves, of radiation, motion of sound waves, motion of cars, automobiles, trains, and planes, motion of people, motion of all the things that we've done in this course is all physics. It's all about things in motion, and physics is such an interesting topic that applies itself to so many different things that hopefully you'll sign up for the 4U physics. It's not nearly as mathematical as this course. It's more theoretical than this course, but again, it opens a lot of doors for you. And if you're going into one of the sciences at university, they will look at your transcript, and if you have taken the 4U physics, they will exempt you from the first year physics. If you're, say, going into a biology program, say nursing, or life sciences, and they will say, did you take 4U physics at Bernie Custis? And if your transcript says, yes, you did it, they'll say, go, check, you're good then. You don't need to do our first year intro to physics. If you didn't do 4U physics at Bernie Custis or wherever, you now have to take our first year intro to physics course at university and pay for it. And it's a lot harder than the Bernie Custis course. So I encourage you all to think really hard about taking the 4U physics. I think you won't regret it, and it will, like I said, even when you're taking it, you may say, I'm not sure why I'm doing this. This is more than I really wanted to be doing. But at the end of the day, it will serve you well, and you will learn a lot of interesting stuff and be able to use a lot of the math that you are studying in grade 11 and 12 math. All right, so I will stop there for now and come back on Monday. So we should do a live class on Monday where I'll take up some of this chapter 18, I'll take up some of the chapter 17, and get us ready for Wednesday's test. So if you're getting this before the weekend, have a great weekend. If you're getting this after the weekend, then know that we are in the home stretch. Okay, bye for now.